Rightio. How much battery do I have? Tight. Maybe I should plug it in to be safe. Better safe than sorry. Okay, next, thermodynamics. If you can write that down, please. Okay, you got that? Yeah, got that? Now, before we start, a little bit of English. So, what does the prefix thermo relate to? What could thermo? Heat, yeah, good. Heat, very good. And dynamics? What's like the word dynamic? What could that relate to or mean? Movement. Like movement. So, what do you think the meaning of this word is, thermodynamics?
Transform.
Change in energy, change in heat, transfer of heat. In other words, how heat moves, how heat behaves. That's what we're looking at here. Okay, so there's a bit to get through for this one. So, formally, thermodynamics is the part of physics that studies the movement of heat between different objects. Now, I think just writing that down is enough. Yeah? Got that? Now, you don't need to write the next part down, but it's useful just to at least hear it. So you also study in thermodynamics the change in pressure and volume, but obviously because that's related to heat. And you also use statistics a lot in thermodynamics because you're looking at the motion of many particles. So it's not possible to look at the movement of every particle, right? There's too many in a gas. So you use some statistics to study it as well. Thermodynamics is useful because it helps us understand the world that's very small, how it connects to the world that's very big. So obviously this cup is very big, but it's made up of many small particles. So you want to know what the relationship is between the big scale, you know, the volume and the pressure and the temperature, and the small scale of the little atoms moving around. Okay. Right. So we've seen that the kinetic energy of an ideal gas, you can find it from this formula. Remember this one? Energy is 3/2 PV. Quick test. Why is the 3 a 3 in the formula? You remember the question, but do you remember the answer?
1/3.
Yeah, but why 3? Why not another number? Why was it a 3 and not a 4 or 5? It was because there's 3 dimensions. Yeah? And you remember the pressure. Where did the pressure come from? It came from the force. And where did the force come from? The wall. The change in momentum when it hits the wall. Okay. Now, you also have this formula, PV equals NKT. Yeah? We just did that one today. So we have two formulas. We can say that the total energy is 3/2 PV, but we also have PV equals N or T. So what happens if I put this formula from today into that formula from last week? So you can get kinetic energy is 3 over 2 N or T. Now, 3 over 2 is a constant, yeah? N is a constant. I mean, for some gas, it's a constant. If you don't let the gas leak out or put more gas in, you know, if you just had a box with some gas in it, this is constant, this is constant, this is constant. Okay, but imagine you could change the temperature if you put some heat into it. So this could change and this could change. So since this is a constant, we can think about it like this: kinetic energy equals a constant multiplied by temperature. Or in other words, you could say kinetic energy is proportional to temperature. Yeah? Now that's quite interesting. So it means as the temperature increases, the kinetic energy increases. Now we have to be a little bit more precise. So we'll do that again, but we'll just be a little bit more accurate. Or maybe I have it here. Yeah, no, I do, but I explained it a lot. So I'll do it in pen. So I want to use the formula PV equals big N KT, because I want to look at all the molecules. Okay, and we know that the total, let's be more clear, the total kinetic energy is equal to 3 over 2 PV. Okay, now I'll put that in there. I get total kinetic energy is 3 over 2 NKT. Now, look what happens if I divide by N. What do you think this is? Total kinetic energy divided by the number of molecules. What would you describe that as? Total energy divided by the number of molecules. What is that like? The energy in one molecule. What would you call that? What name would you give that? No, think more mathematical. You nearly have it. It's just the word I'm looking for. I think you know it. No, I'm sure you know it. Total divided by how many you have. Yeah, what's the word in maths for that? You know this. I know you know it. Average. Thank you, Kim. The average kinetic energy. Yeah? So this is like saying the average kinetic energy is equal to 3 over 2 KT. That's our formula. And if you want, you can write it as a relationship like this. You could also say that the average kinetic energy is proportional to temperature. Now this is quite, well, I'll say it's amazing, but you might not believe me. Quite an amazing result. Because what you're doing is you have a direct relationship between the energy per particle and the temperature of the gas. That's quite amazing, because if I measure the temperature of this, I can know the average kinetic energy per particle, something that would be very difficult to measure. So this is what I'm saying. It's quite, the thermodynamics relates the small world and the big world together. Okay, I think I have the formula here. 2k over 3. That's not quite what I have. I have it upside down. I think I made a mistake here in the slide though. Yeah, I think I made a mistake here, because this one looks right. I think I have it upside down. The formula is 3 over 2, isn't it? Or did I write it upside down? Or is it 2 over 3? It is 3 over 2? Okay, I must have wrote it upside down on the slide. Anyways, this is the result, if you can write that down, and we'll look at the meaning of this. And remember, T is in kelvins. We're using kelvins now. Here, it's so important it needs 3 exclamation marks. That's how interesting it is. Okay, continue. Well, I'll just leave this here, but continue in, we have to look at what this result means. What would I be saying if the temperature was 0 Kelvin? What would we know about the average kinetic energy? There is no. But how, so what are the particles doing if there's no kinetic energy? Still, yeah. So 0 Kelvin means all the particles, all the molecules have stopped moving. So this is why you can't be less than 0 Kelvin, because once the particles stop moving, I mean, what else can they do? Nothing else, you know. If you increase the temperature, then you get more kinetic energy, so they're moving more. Okay. Now there is another way to increase the kinetic energy. You could increase the mass of the molecules, but you're not really able to do that. So more kinetic energy means more speed. Okay. 0 Kelvin means kinetic energy is 0 joules, which means that everything is not moving. It's stationary. So that's kind of interesting. It's not really possible to actually get exactly 0 Kelvin. You can't really, like, imagine trying to make every particle stop moving. It's not really something that you can actually achieve. I believe the smallest temperature ever achieved, if I remember correctly, is 0.16 Kelvin. I think this is the smallest temperature, or maybe even smaller. I'll have to look it up. It's never going to get 0 Kelvin. It's not really possible. It's too difficult. Not even possible, I think. Okay. So we need some more definitions now. When we talk about internal energy, what we mean is and this can be a solid, liquid, or gas, it's the total kinetic and potential energy of every molecule. So in other words, it's the total heat energy, or in other words, the formula, the total internal energy is all the energies of every molecule, which means all its kinetic energies plus all its potential energies. Now, in an ideal gas, we say that there isn't any potential energies. It's just all the kinetic energies, okay? So, yeah, I don't think you need to write all these words down. You can just write internal energy is the total energy of every molecule, which is all the kinetic energies plus all the potential energies. That's the internal energy U. So if you can get this definition as a formula, it would be nice. You can write it down like that. Got that definition, Kim? Yep. You've seen this symbol in maths class, of course, haven't you? Yeah. Okay, continue. So, heat is a form of energy. We talked about this when we did conservation of energy. It is not a physical substance. Heat has no mass. Heat can move from one place to another in different ways. In thermodynamics, heat means energy which is moved between two things. One of them is hotter than the other. Heat is not the same thing as temperature. I know that seems very confusing. You know, you think heat and temperature is the same thing, but it's not. Heat is the energy. You know, so if this is hot and this is cold, and I put them together, some heat energy will move from here to here. Okay. But temperature is, if you remember, is a measurement of the average kinetic energy. It's not really the same thing as heat. Okay. Now, dare I say that temperature is the average speed. It's like a kinetic energy on average. Now, here's an example to explain the difference. So, concentrate carefully. A swimming pool at 20 Celsius has more heat energy than a cup of coffee at 80 Celsius. The swimming pool of 20 Celsius has more heat energy than a cup of coffee at 80 Celsius. Now, why does the swimming pool at 20 have more heat than coffee at 80? Why do you think? What do you think makes the swimming pool have more heat energy than the coffee cup? It's just more particles, yeah. So there's more energy in total. But we say the coffee cup is hotter. So this is a problem with English, okay? Even though we say the coffee cup is hotter, we're talking about the temperature, not the heat energy. So I understand that this might sound very confusing, okay? So when I say this is hotter, I don't mean it has more heat energy, I just mean its temperature is bigger. So it's like we need a different word than hotter, something that means temperature is bigger. I don't know. We could make up one or something. Bigger temperature. What could we make up? Bigger temperature. Thermal bigness. I don't know. Something like this. We need to think of a word instead of hotter. So just to be clear, heat, also called thermal energy, some properties about it. You can transfer it from one material to another material. You can measure it, and it's not a material. Heat is not like a thing you can, hold. And heat is a form of energy. So here's some properties of heat. You don't have to write the full sentence if you just want to write a word or two. So it can be transferred. You can measure it. It's not a material, and it's an energy. You can just write that if you like. You don't have to write the whole sentence. Unless you're Chow. You want to write the whole sentence. Got that, guys? Yeah? Continue?
Yeah.
No, can I continue on that? Continue in a minute, it's okay.
Just a bit.
Yeah, it's fine. Which one are you on?
Last.
Ah, grand. Okay, on deck?
Yeah.
Yep. Right. The heat supplied Q. So, if I put this under a fire, I'm putting heat energy into it. So we call that Q, the heat supplied. And it's the energy pumped into the system. It's like how much energy you push into it. So obviously an easy way to do that is to put it under a fire, or put it on a heater. this is the heat supplied. It's called the letter Q. For example, well, I'll let you write this down first. Okie dokie, got that? So for example, a train engine works because it gets heat energy Q from burning of the coal. This heat is converted into work. So I think I have a picture here that, oh no, not quite yet, maybe in the next slide. So the reason we care about the heat supplied is because when you put heat into a system, you can make the system do some work, which we'll get to in a minute. So you know a train, you all know what a train is. You have them in every country, I believe. So a train works because you're putting heat into the engine by burning the coal. Okay, so it's a useful idea. Okay, definition. Two systems are in thermal equilibrium if there's no heat flow between them. So, my left hand and my right hand, they're in thermal equilibrium because when I put my hands together, there's no heat that moves between them. Okay, but if I was to take something cold, like the board, if I put my hand here, I can feel the heat from my hand going into the board. You know when you feel something is cold? That's what's happening. The heat is leaving your hand and entering this. So this is not thermal equilibrium. Okay? And if I put my hand on something hot, like say the battery here, it feels hot. That feeling is the heat from the battery moving into my hand. Okay? So if there's no movement of heat, we call that thermal equilibrium. Basically, it means two things have the same temperature. So, thermal equilibrium is no heat flowing when there's a connected path that allows the heat to flow. Okay, you'll need this definition, so you can write this down. The path permeable to heat just means the heat has a way to travel, but it doesn't travel because they're in thermal equilibrium. Basically, they're the same temperature. Okay. Got that? Yep. Okay. This is a train. Very simple little picture of a train. So, just to give some... Yes? You've seen these before, haven't you? You're Korean, aren't you? You have these here? Yeah. You know the ones I'm talking about? The smoke comes out the top. Yeah. So, when you burn the coal, you're putting heat energy into the engine. So the Q is the energy put into the engine. This is from the coal being burnt. Okay. The delta U is the change in the internal energy. So what happens to the water? Obviously the water gets hot, and the engine gets hot, and everything gets hot. So the internal energy increases. And the work, W, well, what's the work being done? Well, it's the train moving, isn't it? This is the work that's being done. So, if you think about the conservation of energy, what is the relationship between Q, U, and W? The energy before equals the energy afterwards. So what is the energy before? What is the energy at the beginning? It would be zero at the beginning, but let's imagine everything is up and running. So you start to burn the coal. So what energy do you have at the beginning? It will be the Q. Then later, this heat energy from burning the coal, what is it transferred into? What is it converted into? Yeah, the work, which is the kinetic energy, and what else? Yeah, which heat now? Be precise. What do you think? So, like, think about this is the train engine, okay? It's cold and not moving. Then I burn a fire and it moves. So the Q here should equal the W and the U. This engine is now hot. You know, if you touch it, it's hot. Was it hot before I burnt the coal? No. So the energy from the coal became work and the train became hotter, internal energy. So you could write it as Q equals U plus W. It's conservation of energy. That the energy that goes in equals the hotter engine plus the work done. What you could write down is just the last line. Just the last line. The conservation of energy states that Q equals U plus W. Or to be more precise, the change in U plus W, the extra increase in internal energy plus the work done. Wow, not nowadays.
Some people.
Oh yeah.
Then how does it
So what happens is when the internal energy of the water increases, it becomes steam, and the steam pushes the piston in the chamber there. So the steam comes down and pushes the piston, and then comes out here as steam. So this swings around, and then its momentum carries it back, so it closes again, and then more steam enters and expands it.
What is the normal method?
With the wheel? Yeah, it will be a little bit hard to get the train started, you know, but once it gets moving, it's okay. There's a lot of mechanics going on as well to make sure that you can get the wheel turned enough to get it started. Like, you know, this is like, you know, a complicated system connecting the two wheels. It's not just a simple bar. So when the piston first expands, it has to push it around enough so that it can get going. So you kind of see this with trains anyway. They don't exactly, it's not like a car. It doesn't smoothly start, these old trains. You know, you've got a bit of a bump at the start, but then it gets moving, you know. Okay. Anyway, no trains work like this anymore. Most trains are diesel engines, just like a car engine. Okay. Next now. So in this picture here, you can change heat into work. This is the most important thing about thermodynamics when it was first invented about 200 years ago. You know, it was the study of how to change heat into work, really. You probably learned about this in school. The Industrial Revolution. Do you know what this is? No. It's when places like America and England started to use steam engines in factories and in transport. Is this something you've learned? No? No. Well, think about your own country, okay? In the past, people didn't use steam engines, and then maybe about 200 years ago, people started using steam engines. You had trains, you had factories, okay? This is all because of thermodynamics. You can change the Q, heat, into work W, okay? Heat was converted into work. However, it's possible to do the opposite. You could do work and make heat. James Joule discovered this, and here's a simple little experiment to do this. Let me show you it. Very, very simple. He did this about, 150 years ago, I guess. So, what you have here is a weight. What energy is in this weight? What potential energy? And then it's connected up to this wheel here. So when this falls, this starts to spin around. And you see there's two paddles here in the water. So you have a little bit of water and there's paddles that turn around. Okay? And here is a thermometer for measuring temperature. So if you let this go, it will fall down. This will make this turn around, and you can see the temperature increases. And the increase in temperature is because the potential energy here became heat energy in the water. Because when this hits the ground, it has no potential energy. Where did it go? It didn't just disappear. It actually became the heat energy in the water. Yeah? So that's very interesting. So you can go both directions. You can make heat become work, and you can make work become heat. You can switch between the two. This is very interesting, simple experiment that James Joule did. And at the time, nobody believed him. Nobody thought it was possible to change work into heat energy. Everybody knew you could do it the other way. You could take heat energy and make it do work. But nobody thought you could have work and make it become heat energy. So it was a very big deal at the time, even though it's a very simple experiment. I don't think you need to write this down, but it's just a good example of how you can actually go both directions. Some air is heated at ground level. Explain what the delta U is not zero, Q is not zero, and W is not zero here, and how it achieves this. Why the heck did I put this question in here? I had a reason, but I don't think it was a good reason. What the heck did I put this in for? No, pretend you didn't see that question. Right, okay, so what I want to do is, of course, we have three laws, because, everything in physics that's important has three laws, Newton or whatever. So, we have three laws for thermodynamics. So the first law is not called the first law, it's called the zero law. So we start counting at zero. So the zero law, which is the first one, says, okay, so I'll explain this one. If two systems are in equilibrium with a third, then they're in equilibrium with each other. So I'll explain that in a moment. Okay, let me explain this one. So, imagine I put my coffee cup and my phone touching, and there's no heat transfer. So we say they're in thermal equilibrium, okay? Now imagine I put my coffee cup and this remote touching, and there's no heat transfer. So they're in thermal equilibrium. Therefore, these two must be in thermal equilibrium as well. So it's like saying, if A and B are the same temperature, and A and C are the same temperature, therefore logically B and C are the same temperature. That's all it says. So this is the reason it's the zero law, because it's not very important or interesting. So it doesn't even deserve being called the first law. It's called the zero law because it's not really that interesting. Now on to the real first law. So the first law is that it's like conservation of energy. We've actually saw it earlier today. It says that U equals Q minus W. Now, when I gave it to you earlier, I said Q equals U plus W. Yeah? So I just took the W to the other side. It's usually what's done for these problems. Is that okay? Yeah? Yeah? Okay. So this formula is useful because it tells you, if you look at how much heat energy you put in and how much work you get out, the difference is how much extra internal heat energy you have in your engine. So obviously you actually want this to be small, because if you put Q in and you get W out, you don't want to waste your Q by making the internal energy bigger. You know, if you have a train, you don't want it to get too hot because you're wasting energy heating up the train. Because you don't care that the engine is hot, you only care about how fast it goes, you know. So you like the delta U to be small as possible. And the second law of thermodynamics states that heat cannot flow from cold to hot unless you do some work. Now this is obvious if you think about it. If you're eating a hot apple pie with ice cream on the top, does the hot apple pie get hotter and the ice cream gets colder? No. What usually happens when you put cold ice cream on a hot apple pie, the hot apple pie gets colder and the ice cream gets warmer. This is because the heat in the apple pie moves to the ice cream. It never happens the other way. You never put ice cream in a hot apple pie and then 5 minutes later say, this hot apple pie got hotter and this ice cream got colder. That never happens, right? So this is actually the second law of thermodynamics, that heat flows from what's hot to what's cold. It's so obvious. So obvious, it's amazing it's a law, but it's the second law. Now that's not to say that you can't make heat go from something which is cold to something which is hot. You can, but you need to do some work to do that. Okay? So like, you know, an example maybe, let's say, if, let's see, what could we use as an example? Yeah, so let's say in this room it's quite warm, and outside obviously it's quite cold. So if I was to open the window, what would be the natural flow of heat? Would the heat Leave the room or enter the room? If here is quite hot and out there is quite cold, what would happen to the heat? Yeah, the heat would want to go out. Okay? But you can make a little sort of pump, a little machine, like a air conditioner, that takes the heat from the outside and pushes it in. So then what would happen is, in here, you see, look, all the heat is leaving and now you're feeling cold. So the heat can increase in here and it can get colder outside. But to do that, you would need to do some work. You would need to use some kind of pump. Like at home in your fridge. You know your fridge? Your fridge is a good example of this. If you put something hot in your fridge, the pump in the fridge takes the heat out of the food and pushes it out the back of the fridge. This is called a heat pump. It takes the heat out and pushes it out. Okay. What else? I think like your air conditioner. Your air conditioner, it makes you cool down. It's like it takes heat away from your body and pushes it out somewhere else, like outside the car. You know. So if you want to make the heat go the wrong way, you need to do some work, because naturally you'll get hotter. Naturally the heat goes from the hot to the cold. Okay. Inside your car is a bit more complicated because the heat from the outside goes into the car, but because of the windows, it's like a greenhouse. You know, greenhouse, like climate change. So it gets hotter inside because the sun can come in and the heat can't really escape. So it's a bit different, but similar. Okay, so thermodynamics, there wasn't too much to do. There's lots of definitions. So there's not really calculations, it's mostly just a little bit of calculation. Actually, you know what, Stephen, you're right, it's almost all calculation. Number 6 is my favourite question, because you all know that there's a minimum temperature. What's the minimum temperature? It's 0 Kelvin. This is called absolute zero. But maybe you're wondering, is there a maximum temperature? If you do number 6, you'll figure out the answer. But I'd be right in thinking that next time you might want to do a tutorial, or because we have a couple of lessons done now. We'll see next time then, okay? Right, we'll finish there.
No, we're going to have to get it today. We didn't get it this afternoon.